First of all, thanks a lot for sticking around. It's getting kind of late. This talk will be a little bit different from the other ones. So my name is Alessandro Maggi. I'm the founder of Ecate. And very briefly, I'll give you a quick introduction about my background. I'm not a biologist, so this talk, unfortunately, will not be about biology. I mostly study aerospace and electrical engineering. And so most of it will be kind of electrical, related to electrical interfaces. Today I'd like to tell you a little bit about our approach to longevity. Most of the talks we heard were about biology and how we can harness the power of biology to fight aging. And biology is the best. Most likely in the future, in the long term, is probably the way to go. In the short term, however, it seems very challenging, especially from a non-biology perspective. So what we decided to do was to take a different perspective. And the perspective that we took was that of bioelectronic interfaces. Bioelectronic interfaces have been around since the 60s. So you have pacemakers, ICDs, cochlear implants, brain stimulators. And they've been proven to improve a lot of diseases. So what we wondered was, would it be possible to take a brain and transplant it into a synthetic body and communicate with it bidirectionally? So we know that neurons, for instance, are less susceptible to aging. The fact that they don't replicate helps a lot, but of course they're not immortal. They're still very sensitive to other aging processes, such as oxidative stress. However, at the moment of death, for the majority of people, their brain is still very much younger than the rest of the body. So we thought that by transplanting this brain into a synthetic body, we could expand the patient's lifespan by tens of years, or potentially a lifespan, potentially doubling the lifespan. Of course, this is not simple, and there's several steps that we need to take before we can go from this idea into an actual tangible product. And the first step is actually the validation of our neural interface. This neural interface that we're developing is meant to be implanted at the base of the brain or in the spinal cord. So the obvious validation pathway was using paralysis and paralysis-related diseases, such as neurogenic bladder. So if virtually all patients that suffer from complete spinal cord injury suffer from neurogenic bladder, which is the complete loss of control over your bladder, over micturition. And the current treatments are only somewhat effective. They're mostly based on catheterization. Catheterization is effective, but doesn't prevent urinary tract infections. And urinary tract infections is the main reasons why SCI patients end up in the hospital. And more importantly, 80% of patients are dissatisfied with this treatment. So a better alternative is actually sacral nerve stimulators. And these stimulators basically use electricity to stimulate the sacral nerve, which then squeezes the bladder. So these patients can somewhat control their micturition. But an even better approach would be using brain-machine interfaces. You can imagine a brain-machine interface that can warn the patient about their bladder being full, so then the patient can find a bathroom, and then when they want to urinate, the brain-machine interface would help them do exactly that. Brain-machine interfaces actually have advanced tremendously over the last 2 decades. There's companies like Paradigmics, Neuralink, Synchron that have shown that we can take BMIs and turn into actual tangible medical devices. BMIs have also been shown to allow paralyzed patients move cursors on a computer or robotic arms. And more recently, a company, Paradigmics, have been able to fabricate a device with 65,000 channels that can be read out simultaneously, which is a tremendous advancement. However, all these BMIs suffer from drawbacks that are inherent to the brain structure. As I'm sure you know, the brain is made of billions of neurons that communicate three-dimensionally over a pretty large area that spans several centimeters. And more importantly, millions of neurons are required for these neural networks to form and then give rise to behavior. Because the structure of the brain is so complex, thousands of electrons are necessary to try to understand what the brain is trying to do. And not only that, but you also need really complex decoding algorithms and really fast data rates. Just to give you an example, the data rate that Parajomic uses is 20 gigabytes per second, which is what your cell phone uses when you talk to someone, which is an immense amount of data. And when you have immense amount of high data rate, this causes a lot of power consumption, and power consumption leads to heat evolution. And if you talk to anyone in medical devices, heat evolution is really bad news because it can cause damage to your tissue. So the solution to this is using heat sinks, but heat sinks are really huge. So you end up with a device that might not heat up your tissue, but is really big, which is also another issue for medical devices, and a concern in terms of safety. So overall, interfacing with the brain is great and has great potential, but also poses significant challenges. So on the other hand, if you interact with the spinal cord, things get much, much simpler. So this is, as you know, this is the spinal cord. Spinal cord is composed of a central area, a central core of gray matter surrounded by white matter. The white matter is substructured in exon bundles, and these exon bundles are conglomerate of axons that work all together. They fire all together when a certain body part is activated. And they show something called somatotopic organization, meaning that the sensory and motor activity is discretely organized and spatially organized within the spinal cord. Basically, these axon bundles form a map of the body into this tiny space of the spinal cord, which is 3 orders of magnitude smaller than the brain. So we decided to take advantage of it. Aside from this, inherent map, the communication between the brain and the body within the spinal cord and, well, within the white matter of the spinal cord is one-dimensional. So you can imagine it's much easier to deal with something that is one dimension rather than 3 dimension. So overall, interacting with the spinal cord allowed us to make a simpler, smaller device that doesn't need thousands of electrodes, complex algorithms, or fast data rate. So basically what we're trying to do is a relay station for the brain, and this is why we think that it really fits with trying to treat paralysis. In paralysis, the communication between the body and the brain is severed. So if we can build a relay station that bidirectionally, that restores this bidirectional communication, we can potentially solve or partially solve paralysis. The interface that we're trying to build is meant to be implanted right above the site of injury and is able to understand what the patient wants to do through decoding, not really decoding, through sensing the action potentials coming down from the motor tract of the patient. And we're also able to restore sensation in the patient by stimulating the sensory pathway of the spinal cord. And so this device can really be potentially be used to treat several paralysis-related conditions, such as restoring movement, micturition, bowel control, and sexual functions. So here's, in the next few slides, I'd like to show you how our probes are made and early data we got in vivo. So these are our probes. As you can see, they're made from silicon using a standard CMOS and MEMS fabrication techniques. We can make single or multiple shank probes. Each shank is about 3 millimeters in length, 400 microns in width, and only 30 microns in thickness. So then when we insert, we minimize the damage when we insert. And we have these electrode arrays that are housed within the shank. And these electrodes range in size from 15 to 30 microns squared. And in terms of sensing electrode, we also have a local reference electrode that helps us decrease the noise and virtually eliminate local field potentials. So morphologically, we're able to make 2D electrodes and 3D electrodes. These 3D electrodes are mostly used for stimulation, since when you have 3D electrodes, you increase the surface area of your electrode, which increases the availability of charge to stimulate axons. And this is really important because you want to try to minimize the charge you put in the axons. You still want the axon to fire an action potential, but you want to minimize that charge to decrease the chances of creating damage either to the tissue or to your electrodes. On the electrical side of things, For the sensing scheme, we use we try to simplify our chip as much as possible. So on the sensing side, we have a relatively narrow band AC coupled dual stage amplifier followed up by a comparator. This comparator takes the neural signal and digitizes it into a sequence of ones and zeros. So if you have an action potential, you get a 1 out, or if you have baseline activity, you just get a 0 out. And on the stimulating scheme, we developed a chip that is pretty standard current-controlled stimulation at different frequencies. But an unusual feature that we added was the ability to have dual frequency mode, where we have a high-frequency stimulation pulse that rides along a low-frequency carrier wave. And we observed that this dual mode was much more effective at eliciting action potentials than using only high-frequency or low-frequency stimulation. So this is an example of our bidirectional interspinal probe. As you can see here, you have on one shank, you have both the sensing and stimulating electrode array. We have 2D electrode arrays that we use for the sensing part of the array. These 2D electrodes are coated with high roughness platinum, as you can see it here. And then we have the stimulating electrode array, where you see the 3D electrodes in terms of, we use nanocones in this case for stimulation. If you look at the impedance spectrum, we can see that we were able to decrease the impedance of our 2D electrodes to about 80 kilo ohms at 1 kilohertz. And just to give you a reference, if we had smooth platinum, this value would be about 300 or 400 kilo ohms. And this value is really important, is really related to the RMS noise that you get during recording. So when you decrease the impedance, your RMS noise also decreases. So we were able to achieve 10 microvolts of RMS noise, which for in vivo consideration is pretty decent. On the stimulation side, we used 3D electrodes, so black silicon-based platinum electrodes. And because of the 3D features, we were able to further decrease the impedance of the electrodes to 30 kilo ohms at 1 kilohertz and achieve a charge storage capacity of 10 millicoulombs per centimeter square. And again, for reference, this is about 1.5 orders of magnitude higher than if we had to use simple 2D electrodes. We then tested our probes. We then tested our probes in vivo in rats. We wanted to determine whether we were able to sense action potentials and elicit action potentials. So this is our setup. Our setup involved a laminectomy, durotomy, and then for the sensing experiments, we insert our probe with the electrode array facing caudally, so facing the tail. So then we were able to use mechanical stimulation to elicit action potentials. And the idea here, the goal here, was to create a one-to-one map between the location of the mechanical stimulation and the location of action potentials within the spinal cord. Of course, for the sensing part of the experiments, we inserted the probe in the sensory part of the spinal cord, which is here in the dorsal area. And this is a representative recording that we obtained. We see that most of the channels actually don't show any action potentials except for a few, so in this case, this one. This is really important. It shows us that our recording electrodes are selective enough to be able to discriminate different parts of the rat's body. So then what we did next was we took these recordings and mapped them onto the spinal cord to create this one-to-one mapping. So here, the silhouette is a schematic of the rat sensory area of the spinal cord. And then the heat map represents the electrode array. So where you see blue is where we saw the action potentials. So for instance, when we stimulated the gluteus, we see that the action potentials were in this area. Or when we stimulated the leg, the action potentials were further down, more laterally. We were also able to obtain proprioceptive information. And to do this, we moved the rat's leg in two different positions. So we went from a resting position to an adducted or abducted position. And we noticed that as the leg was moved into two different positions, the frequency of the firing pattern changed dramatically. So we're able to recreate the sensory map onto the spinal cord and also obtain information about proprioception. The same thing we had to repeat for stimulation. So since we want this probe to be bidirectional, we need to be able to sense action potentials, but also elicit action potentials. So we We validated stimulation both rostrally and caudally. So rostrally in a sense that we stimulated from the lower part of the rat's body toward the brain, and then caudally we do the exact opposite, so from the upper area of the rat's body toward the tail. The upper part of this slide is concerned with rostral stimulation. So we implanted our stimulation probe downstream of the sensing probe, and then we stimulated. The goal was to be able to elicit action potentials from the site of stimulation and have this action potential traveling toward the brain. And more importantly, we needed to make sure that these action potentials were confined, spatially confined. And this is exactly what we saw. So here, this plot shows, well, first of all, these black dots is the stimulation artifacts. And then we see that only one channel recorded by the sensing probe showed action potentials. And this is really crucial because if you want to stimulate, let's say if you have a patient, a spinal cord injury patient, and you want to have this patient feel that their bladder is full, you need to stimulate the axon bundles that is responsible for micturition. So we really need the stimulation to be very confined. If it wasn't, the patient would feel a bunch of inputs that might not be related to micturition. So we were able to demonstrate this. So we were able to demonstrate that we can selectively stimulate rostrally. We repeated the experiment this time in the opposite direction. So we stimulated from the upper part of the rat toward the tail, and we wanted to see if we were, again, be able to selectively stimulate axon bundles. And in this case, we monitored how selective we were by looking at how many muscle fibers we were able to activate. And similarly to what we saw before, we observed that, again, we were able to be pretty selective with stimulating muscle fibers. In this case, for example, here, we were able to selectively stimulate the tibialis anterior and not the other muscles around it. So overall, we confirmed that we were able to sense action potentials and also elicit action potentials bidirectionally. So the encouraging results that we got from rat experimentation led us to the development of our proof of concept device, Biomic, so bionic micturition, that combines a very established technology, which is sacral nerve stimulators, with our intraspinal probe. So the way the device works is very simple. We have a bladder sensor that monitors bladder volume. When the volume reaches a certain threshold, a message is sent to the intraspinal probe. The intraspinal probe at that point stimulates the sensory pathways, the sensory micturition tract of the patient, so then the patient can feel that they have to find a bathroom and go pee. At the same time, when the patient wants to urinate, this message is set down the spinal cord, sensed by the intraspinal probe, which sends up then a message to the sacral nerve stimulator that then squeezes the bladder and urination can happen. This is very briefly, I'll go through this. This is the early validation that we've done in rats. We've been able to map both the sensory and the motor centers for micturition. Then we were able to correlate action potentials coming down the motor tract to avoiding events. So here you see this graph shows pressure in the bladder, and this one is the raster plot of the action potentials that we obtained. As you can see, the action potential in a specific part of the spinal cord, this part, always preceded voiding events. So we're pretty confident we can understand when the patient, or in this case, when the rat wanted to pee. And at the same time, we were also able to evoke micturition events also in the rat by stimulating the sensory micturition pathways. In this case, you can see here these vertical lines correspond to the stimulation artifacts. And they always, as we stimulated, right after stimulation, we had voiding events. And this was very consistent across rats. We've done these experiments in acute settings and chronic settings in rats, and now we're moving toward larger animals. And with this, I'd like to thank our team. We have a mixture of more electrical engineering side and the medical side. and our sponsor, NSF and NIH, and I'd like to take some questions.
Phil disappeared, so I'll do this for him. Any questions? Where's the microphone gone? Oh, I've got it over here.
Fascinating stuff. There's been reports from other patients who've had metal chips inserted into the brain, and the brain has kicked them out again. How confident are you that the kinds of probes you're inserting will stay, or is there a future in which you have more bio-friendly materials for these connections?
Yeah, so this is a great question. So, and that's a tough, I mean, the answer is pretty difficult. So right now, the only things that have been implanted in patients were black rock devices like the Utah array. Utah array is really rigid and quite large. It works, but of course it works acutely. Chronically, it's hard. You get a lot of encapsulation. The Neuralink device is much more flexible, but it's it's under clinical trials right now, so it's kind of hard to say. The spinal cord is less capable of encapsulating devices, but it's difficult for another reason. The spinal cord moves a lot. So keeping those probes inside is not easy. We have our way, but we've only done it in rats in a chronic setting. And so we're hoping to go into humans in 2026. But this is definitely something that is hard to say for sure will work. So it's making the device as flexible as you can is going to be part of the answer. But I'm not sure it's the full answer. But yeah, it's a great question.
Any other questions? Yep, over there.
Yes, thank you very much. This is very intriguing work. Now, to the broader question as to whether a brain can be placed in a robotic body, I'm wondering if a viable intermediate step toward that might be to transplant a mouse brain into a robotic mouse body, considering how many mice get euthanized at the end of particular studies. It might be a readily accessible source of mouse brains instead of just ending the lives of these mice to try to prolong them by providing robotic bodies for them. How far away do you think we are from those kinds of trials?
So that's a great question. So of course, that's the idea, to go into rats. Mice are too tiny, and rats are really difficult, but still feasible. But first of all, we just wanted to make sure that this could even work. There are challenges, like, for example, having the probe maybe coming out. Other challenges like Valerian degeneration, that's also not a problem. So we wanted, and that's why we're going, like we're taking baby steps, and we're going for the micturition first, and then restoring movement. But finally, yeah, that's a goal. And in terms of how far, we could do it tomorrow. It's not really how far, it's do we want to do it tomorrow? We think that it's smarter to figure out whether the electronics work first, and then if that works, then we can move on to that. It's moving into that in terms of the medical side, and I'm not a physician, so I'm just telling you what our neurosurgeons told me. That seems, especially in mice, it seems not that hard to do. But on the electronic side, we really need to make sure that this works before moving forward. And we think that this device for spinal cord injury patient is the best way to make sure that the device works, because once you have a complete injury in the spinal cord, that area becomes pretty much inactive, especially like a few millimeters around the area. So there's very little risk going into the spinal cord of the patient. There's still risks, but much fewer than in the brain. So that's kind of like, those are kind of the steps we want to take, make sure that the electronics work, and then go into rats and try this, yes.
All right, thanks, Alessandro.
Thanks.